By August 2026, a relentless heat wave pushed temperatures in Europe and North Africa to a record-breaking 41.2 degrees Celsius. As millions of people simultaneously cranked their air conditioning to stay safe, the surge in demand met a failing supply. In France and Romania, major districts went dark as regional grids began to trip. The scale of the failure was total in Cuba, where the entire national electricity system collapsed, leaving 10 million people without power or running water. It's easy to assume the electrical grid is a dry environment, a system built solely of wires, metal transformers, and solid fuel. But drought creates a physical bottleneck for electricity, directly threatening the infrastructure we rely on to keep the lights on. Most of our electricity is generated through the same basic process. Whether using coal, gas, or nuclear uranium, power plants generate heat to boil water, creating high-pressure steam that spins a turbine. For that turbine to keep spinning, the steam must be condensed back into a liquid state to maintain system pressure. This cooling phase requires a constant intake of cold water, millions of gallons pumped from a nearby river to absorb the excess heat. In August 2026, this cooling source vanished. Critical waterways like the Rhine and the Danube dropped to historic lows, exposing riverbeds unseen in decades. The retreat was so extreme that rusted Nazi-era warships, scuttled during World War II, emerged from the shallow waters of the Danube in Serbia. When rivers are this low and the water too warm, power plants cannot condense their steam. Generation physically chokes, and the grid begins to fail. At Hungary's Paks nuclear plant, the dropping Danube brought the facility within millimeters of its absolute minimum intake threshold, merely forcing a total emergency shutdown. In Slovenia, the Kursco nuclear plant was simultaneously forced to throttle its output to 80% capacity, as the Sada River became too shallow and warm. This creates a fatal imbalance. Generation is forced to scale back at the exact moment air conditioning units are driving peak demand across the continent. When supply cannot match demand, grid frequency swings wildly. This chart shows a stable system suddenly oscillating as balance is lost. These fluctuations trip safety relays, automatically disconnecting regions. In Pakistan, a single transmission fault triggered this domino effect, causing a massive national blackout. Because our power networks are linked over vast distances, a localized water shortage can rapidly transform into a nationwide infrastructure collapse. A grid collapse destabilizes the long-term financial health of national power networks, creating costs that last long after the lights come back on. This instability triggers a self-reinforcing cycle, the utility death spiral. First, heavy industries move toward self-supply with private backups. This mass defection drains public utility revenue. Starved of capital, utilities cannot maintain infrastructure, ensuring the fragile grid fails again. The consequence is social and political unrest. In Libya, persistent blackouts have led to daily street protests, with citizens demanding accountability for unstable electricity supplies. Building a resilient grid for a hotter, drier future requires moving our electricity generation away from shrinking river systems. The physical connection between water and power is a vulnerability we can no longer ignore.